So good afternoon. I'm Trey Obering. I'm Executive Vice President at Booz Hamilton, and I'm very pleased to be able to moderate this important panel on directed energy, technology, and manufacturing readiness this afternoon. Now, one would think that the use or interest of the use of directed energy in warfare would be a fairly recent technological event. However, in the 2nd century BC, the Greek scientist Archimedes is believed to have actually used reflected sunlight to burn Roman ships. Nikola Tesla, a noted inventor, scientist, and engineer, developed early high-frequency radio technologies and worked on plans for a directed energy weapon as early as 1900. In 1937, he actually composed a treatise entitled The Art of Projecting Concentrated Non-Dispersive Energy Through Natural Media Concerning Charged Particle Beams. And in World War II, the Germans conducted extensive research on X-ray and microwave weapons. So we fast forward. During my tenure as director of the Missile Defense Agency, we were able to achieve first flight of the megawatt-class airborne laser, shooting down both a solid and liquid missile in 2010 before that program was later canceled. So, as was alluded to several times today, how far have we come in directed energy, really? Where are we today? We've heard some examples of uses, both by the Army, the Navy. We got to drill down now, and let's get into some of the more technological underlying challenges and issues that we still face. In order to do that, we have a great panel here to do that. To my immediate right is Major General Tom Masiello. He's the commander of the Air Force Research Lab. He's responsible for $2.1 billion in Air Force Science and Technology program and an additional $2.3 billion in externally funded research and development. He's also responsible for leading a government workforce of approximately 6,000 people in the laboratory's 9 component technology directorates and the Human Performance Wing. He's a command pilot. He's logged more than 3,300 hours in more than 20 different aircraft. To his right is Mr. Keith Englander. He is and was my chief engineer at the Missile Defense Agency. In this capacity, he serves as the agency's single technical authority for all matters related to the technical planning, development, and integration of the ballistic missile defense system. This includes responsibility for system and element engineering, generation of system and element test requirements, etc. To his right is Dr. Thomas Killian. He's a director in the Office of Technology at the Office of Naval Research. In this role, he's responsible for policy, planning, resources, and execution management for a substantial portion of the Department of Navy's science and technology budget, including the future naval capabilities, the Navy's Small Business Innovation Research and Manufacturing Technology programs. Before joining ONR, Dr. Killian served as director of the Biometrics Identity Management Agency. And Dr. Rich Bagnell, on the end, is the SHIELD program manager at Air Force Research Lab. He was formerly at the Strategic Technology Office at DARPA, where he focused on the development of compact, high-power solid-state laser weapons and a beam director for laser weapon employment. Previously, he held a variety of senior positions in the Directed Energy Directorate of AFRL as well. So I would invite the panelists to give their talks, and then we'll open it up for questions. So, Tom?
Okay, well, thank you, sir. Well, good morning. And I'd just like to say thanks to Booz Allen and CSBA for putting on a fantastic event. The morning so far has been great. I'm going to give you a little bit of a talk real quick on just from an AFRL perspective, what we're doing to advance the state-of-the-art of directed energy, both lasers and high-powered microwaves. So if we can go to the first chart. And I have to agree with a lot of what the other speakers have talked about in terms of being at a tipping point, being at a cusp in history here in terms of actually fielding directed energy weapons. We're at a point where we have a heavy and significant tech push, and at the same time, a significant tech pull from the warfighter. And when you get both of those working in concert, that's where you can make real advancements. You know, earlier when we talked about it, General Harris talked about the Air Force kind of made their bet with chemical lasers. And rightly so, given the state of technologies. With chemical lasers, you get a lot of power. The problem, though, it wasn't really operationally relevant to be deployed Air Force-wide, given you need a 747 worth of hazardous chemicals to make it work. And now with the advancements, significant advancements, just over the last few years in electric and solid-state lasers, really make that feasible. And then with the combination of tech push, again, it's just not the scientists and engineers, it's just not us playing in our AFRL sandbox. You also have the tech pull and then industry. Industry is a big key because nothing really transitions from a lab to the field. It goes through industry. And industry understands this tech pull from the warfighter. They understand, okay, this is something that they're serious about. And as a result, you see a lot of internal research and development money, profit being spent, basically industry spending their own money to advance this technology. Very powerful time in history, I think, for directed energy. Now, on my slide, the Warfighter Panel very well articulated the capabilities that lasers can bring to the battlefield, as well as high-power microwave. And I would like to mention CHAMP. It's been brought up a few times. I'll be honest with you, I don't remember what CHAMP stands for, what the acronym is, but it was a air-launched cruise missile fitted with a high-power microwave package. It flew against several different, well, actually 2 major targets, but was able to conduct several different runs, and very successful. That occurred in October 12, and really the maturity, that demonstrated the maturity level of a high-powered microwave weapon sufficient to go into a program of record at a sufficient risk level if the decision was made to go there. So I'm going to cover 2 roadmaps. I'll cover the laser roadmap and the high-power microwave next. Let's go to the next slide. So this is our overall roadmap, technology roadmap for the developing of high-energy lasers to be integrated on air platforms. The first stair step is the SHIELD demo, and the SHIELD stands for Self-Protect High-Energy Laser Demonstration. And Dr. Bagnell, he'll be able to give you more details when it's his turn here on the panel. But essentially, we're integrating a laser, a solid-state laser in the tens of kilowatts. I would deem that in the mid-power range, into a pod to be fitted on a fighter-sized aircraft. And really, with that amount of power, we're looking at mostly defeating sensors, adversary sensors, and also, as a direct result of General Heithold pulling significantly on integrating some sort of laser on a C-130 platform, we're also going to look at the soft ground target defeat to support that effort. And then as you go out, up the stair step, and the stair step in this environment, I'll just say, is between 5 and 10 years. We can talk in more detail in the classified environment in terms of time frames, but stepping up from a mid-power laser up to, in the 100 kilowatt class, getting into the high energy laser area domain now to defeat, again, this is more defensive in nature, to defeat threats at a moderate range. And then as you go up to the third step, they're talking 300 kilowatts, definitely a high energy laser to conduct the full gamut of military air operations, both offensive and defensive. One thing I would like to point out too on the laser, although obviously we made the shift from chemical to solid state and electric lasers, that doesn't mean all that work that wasn't done was in vain. Hardly so. In terms of the beam control, acquisition tracking, the optical trains, those sort of things, all that is directly transferable to the new laser source that we're looking at. So that is just a real quick overview on the laser side. Let's go to the next slide. And this is a high-power microwave. So the first, we've already accomplished, again, demonstrated, I think, the military utility of a high-power microwave system at a sufficient technology maturity level to be fielded. So where we're going next is improving a CHAMP-like payload to increase the overall effectiveness and maybe the ability to steer it more precisely than the original CHAMP. And then going up the stair step, next would be looking at various other platforms other than the air-launched cruise missile, And then finally, I think everyone recognizes the utility of having a reusable platform and thus integrating it on some sort of either manned or unmanned aircraft that can be reused. So that's the overall two roadmaps. What I'd also like to address is some of the issues that came up this morning, that from an Air Force Research Lab perspective, we just don't believe if it's our job to develop the technology itself, mature the technology, and then get it to a point where it can be integrated onto an air vehicle in an operational environment. I mean, first of all, yes, the technology has to be effective and operationally relevant. I already talked about really from a chemical laser was not operationally relevant across the entire air domain. It has to be affordable once it goes into a program of record. But really, a lot of the policy issues that came up today, that is something that's important that we tackle as well. Well, first of all, the military utility. For kinetic weapons, we understand the effectiveness very well. We're able to predict what kind of kill mechanism we'll get against the various targets. Well, it's important that we develop that same sort of analytical tools to the warfighter so they understand the overall effectiveness in a military environment based on how these weapons are used. The bioeffects. Bioeffects is a significant part of our portfolio because we got to understand the effects of both lasers and high-power microwaves on humans, both as blue force and as well as potential adversaries. And then the policies. There's significant policy issues. If you take a total risk-averse position, you would not want a single photon to make it in the LEO that it might damage one of our satellites. Well, what we are working on are the analytical tools so that you can make a data-based, risk-managed assessment on how you can employ these weapons. The last thing we want to do is have the technology, but the policy and the rule set allows you from taking full advantage or nullifies the effect that you're trying to get. So with that, sir, I'll stand by for questions and pass it on.
Keith?
Okay, I'd like to also thank Booz Allen Hamilton and CSBA for sponsoring this event. And I also want to say this has been a very interesting and great morning. I've learned a lot myself just sitting in the audience. If we can go to the next slide. This gives what Missile Defense Agency is looking at from a standpoint of a notional boost phase engagement, one of the scenarios that we look at. But what you see on really the left-hand portion is really our conventional hit-to-kill system that we have deployed out there now, which is really looking at defending in the mid-course phases of flight. But we all have known since the early 2000s and late 1990s that if you really want to kill threat missile, ballistic missile, you want to kill it in the boost phase. That's probably its more vulnerable location. It hasn't deployed any countermeasures, or you don't have the hardened reentry vehicle to worry about. So what you see there is what we would say is we would add a high altitude type of high energy laser. The high altitude is geared toward not having to worry about the effects of the atmosphere, which is one of the areas that we found to be, I'll say, interesting with the airborne laser platform that we had on the 747. So we want to get higher. And if you go higher, you can also go to a lower power laser than what we were looking at on the airborne laser. If you go to the next slide. So we're working on really focusing on two major technologies thrusts right now. One is at Livermore Labs, the diode pump alkali laser, and then the other is up at MIT Lincoln Lab, which is the fiber combined laser. We're also working with the Air Force with the fiber combined and DITRA in that area. But you can see some of the technical hurdles that we have right now. And we're really at probably a technology readiness level right now of somewhere between 3 and 4. And we're gearing, trying to get to, before we get to a demonstrator, flight demonstrator, somewhere around 6. But for the, what we call the DPALs, laser on the left, really those are the 3 main areas. We pretty well believe we've licked the cell contamination issue that we had. But the key is that we want to take these technologies and transfer them over to industry and work with industry on developing our next step in our technology plan. If we go to the next slide. As I mentioned, we're looking at a laser demonstrator. Initially, we're looking at low power concepts. Low power, we're talking in the tens of kilowatts of energy to do acquisition and tracking and pointing against threat missiles, and you can see some of the candidate platforms we have there. But we also want to go to the higher power, which really is getting into the kill phase of boost phase. And that is something that we're looking at possibly initially flight testing in the 2020 and 2020 plus time frame. But the key is to transfer to industry these efforts. And we currently have a small effort with industry. It's just a 6-month study efforts in order to look at that idea of scaling to a higher power in the future. Next slide. So when you look at it, really the takeaway on the bottom, and I think it was said by most of the presenters today, is that we just got to get on with it. We've been piddling around with it as a science project, I would say, and technology over the past several years. We need to move on and get into actually demonstrating the capability in the air and actually prove out that we can do it with the solid-state lasers, just like we did with the chemical laser on ABL. Next slide. This is our look at directed energy funding that we have right now. You can see back in the late, from 07 through 010 time frame, we were focused on the airborne laser, and then on the right-hand side, we're really looking at the directed energy research work. So we have funding going into this effort, but we're looking at the increased funding, as you can see out there, in order to demonstrate the system. Okay, I think that's my last slide that I have. Yes, so
Okay,
that's it.
thank you. Dr. Killian?
Well, good morning, and I want to thank you for the opportunity to represent my boss, Admiral Winter, who's the Chief of Naval Research, and talk about the work at ONR. The good news for me is my briefing has already been given between comments from Admiral Fuller regarding the work on the Ponce, what we're going to do in SSL tech maturation, SSLTM, and the comments from the Secretary of the Navy. They've essentially covered everything in my slides. So you already know about our programs. That's a great thing. Our partners and our leadership recognizes the importance of this technology, and they're helping us actually get it into the field. And you'll hear from Captain Zud this afternoon, who's a strong partner from the NAVSEA side, on the PM side, in working with us on EM railgun as well as directed energy weapons. So it is a strong partnership between ourselves, our partners who help in the acquisition and fielding, as well as industry partners who are going to make this happen. I'll run through these charts quickly just so you know which programs I wanted to highlight today, but I won't spend a lot of time on them. The main thing I want to do is frame how this fits within the overall ONR S&T program. So next chart, we talk about our program in what's called the 4-box chart. I own the left 3 boxes in terms of the investment in S&T at ONR as Director of Technology. So quick reaction S&T, things that we do within the first couple of years demonstrate a relatively mature technology. The example there is the laser on the Ponce, where we took essentially off-the-shelf solid-state fiber technology and took it to the field to do some work in an operationally relevant environment. Did that within a couple of years, and as you heard from Admiral Fuller, we're going to continue to exercise that as long as that platform is deployed. Tech maturation, the primary program there are future naval capabilities. That's where there's an actual program of record who is a customer who's waiting for our investment in technology to mature, and we're prepared to hand that off to them via tech transition agreement. An example there is the ground-based air defense, directed energy, on the move, FNC, long title. But basically that's a marine application of the 30 kilowatt laser for ground-based air defense, primarily against soft targets like UAVs. Now, the next program is really a mix of future naval capabilities and what we call our innovative naval prototypes, INPs, or which are tech push programs, which don't have a customer waiting for them yet. So there's the hypervelocity projectile, which is a component of the EM railgun program, but is also being handed off to conventional gun partners, which is why it's an FNC, and the EM railgun program, which is building the power and the barrel and the power management systems and everything else to field a system that we're going to demonstrate on JHSB next year. And then last but not least, it's actually a leap ahead program, is the solid state laser tech maturation. It's the next generation solid state laser. We're still in the competition phase for that program. I can't say a whole lot about it, but that's in the 100 to 150 kilowatt class. So more stressing targets under more demanding conditions than what we can get with the 30 kilowatt system. So following this are a series of charts. I'll just show them to you quickly. Hopefully you'll have access to them on the website after this is done. Next chart, that's about the laws, and as you can see there are plenty of videos on YouTube with regard to the work that's been done in the Gulf with the laws system. Next chart. GBADS, that's the Marine Corps application of that 30 kilowatt laser in a ground-based air defense, and you can also find that on YouTube. Dangerous place, YouTube. Next chart. The SSLTM, as I said, currently in competition, up the power levels in the integration to provide capabilities against a broader range of targets. Next chart. And then the railgun, Captain Ziv can talk to you about that in great detail this afternoon, I'm sure. This is about the various components of the railgun itself, the barrel, energy storage, et cetera. Next chart is the collaborative effort that we have in terms of the hypervelocity projectile and demonstrating a ground-based variant with our partners in OSD SCO and with the Army. Next chart. And there's my name and contact info for follow-up.
Okay, thank you. Dr. Bagnell?
Thanks, Tom, and General Oberg. So I'm going to talk a little bit about how we got to where we are today. General Heithold mentioned during his talk the advanced tactical laser. While I did work some on the airborne laser earlier from 95 to around 2000, I was fortunate to be able to get to SOCOM as my last tour. And at the tail end of SOCOM is when advanced tactical laser started. As many of you know in the audience, but some don't, that was a chemical laser on board a C-130. It started at around 2003, finished up with testing in 2009. And we took a lot of lessons learned from that effort. So the takeaways. First, we need to make the laser smaller. On ATL, we exceeded and had to get a waiver for gross takeoff weight in order for us to lift off with that sole weapon system on board. And that was certainly not going to work for the AFSOC operators that needed to use this system. So we put a goal in to try to reduce the size of that system by a factor of 10. And I'll talk a little bit about where we are on that in a few minutes. The other was to make them more capable, to get more power, to get more reach, to get better logistics, because actually the chemical laser had a very limited magazine. It was on the order of 5 to 6 shots. I think it actually fired 6 shots once, and then it would be returned to base. That was unacceptable in the warfighter's perspective as well as from the technologist's perspective. So we needed to get something better than that. Electric lasers were an opportune place to get that. We believed, and still do, that with electric lasers we should be able to go to nearly unlimited magazine as long as we have fuel. So that was one way to go. And as well, we needed to make sure that these systems were reliable. Of course, the chemical laser approach, a lot of plumbing besides the optical engineering that needed to go on. And as a result, it was a complex system. Availability was not as good as we'd like. Operational suitability, and as well, on advanced tactical laser, we had a limited field of regard. So if it was to be used for defensive applications, we needed to expand that field of regard so that we could cover the entire, at least lower hemisphere of the aircraft. Those things I took with me when I went to DARPA to begin working on a couple of projects. One was HELADS, which was mentioned earlier today, the High Energy Liquid Laser Area Defense System. See, now it rolls off the tongue. Before it was not that easy. So that system has been demonstrated and at publicly releasable level is now at White Sands Missile Range. One of the vague descriptions that was early on that they didn't want to tell you about what's going on at White Sands, but DARPA did publicly release that we sent the laser down to White Sands. It is in the throes of integration right now. We're expecting that we will be demonstrating in the next couple months with that system. The other program was called Aero-Adaptive Aero-Optic Beam Combining, and actually the former PM for that, Tom Beutner, is in the audience as well. I have to thank him for that program, a very interesting program to work, very successful, and it actually is the seed for, or the results for that system are the seed for what the SHIELD ATD, again, SHIELD, General Masiello mentioned, is Self-Protect High Energy Laser Demonstrator. The idea there is to be able to equip an airborne aircraft with the ability to counter inbound missiles from any pointing angle. As far as lasers are concerned, there are a lot of lasers in development, or at least 3 or 4 that are in development that we believe can be germane to that mission in the next 3 years. We haven't selected a laser for this system yet. The first part is the hard part, at least from a beam control guy's aspect. Beam control is the hard part because we believe that lasers are mature enough for us to be able to use close to what's available right now to do most of the mission that we are going after. And as a result, we're going to work on beam control, the ability for us to be able to get past the atmospheric distortion that prevents us from getting a lot of power density on the target, melting the target, and then affecting the kill. So all of that came from, at least my motivation, came from what happened on the Advanced Tactical Laser. So I believe that we have much of the technology in hand or nearly in hand for us to be able to handle the self-defense mission that both ACC and AFSOC are after. And that's what the SHIELD ATD is going to be about. There's been a lot of work as well at Army and at Navy on ruggedization. The Army's HEL-MD has demonstrated that they can get a laser system, or at least a surrogate laser system and a 10 kilowatt system on board their HEMIT platform and demonstrate effectively against a variety of targets, including UAVs and mortars. And in doing that, they've shown that their ruggedization works. The even more impressive is the quick reaction force capability that the Navy has been demonstrating on Ponce. I hadn't realized that it had been so long since it went on board the Ponce, and so long since it's come back, and it's still operating, and the operators are still enthused about what it can do. So that's good news. Part of what I did at DARPA after we were pretty sure that the laser was going to be working was to go out to a couple of performers and see if we could get a preliminary design for how big this system might be on board, just with the Generation 1, the first generation HELAD system that is now at White Sands. And it worked out that both performers came in that they would be able to do this in about 10,000 pounds, which is maybe not impressive, but now maybe more impressive that General Heithold is willing to go to 10,000 pounds. So we had them come up with preliminary designs, one to put on the B-1 for penetrating bomber work, one to put on the C-130, advised by what I'd known from the ATL, one to put on a family of military vehicles for the Army, and one for each of the littoral combat ship and the DDG-51 that you see at the bottom there. What we learned from that is that the laser is no longer the long pole. It's power and thermal. It works out that power and thermal to supply this laser, which is not the highest efficiency laser that you might be able to get. Joe Mangano's working on that over at DARPA and trying to get us to even smaller, better efficiencies in smaller lasers. But even with this laser, the power and thermal required is 3 to 4 times the size of the laser itself. And so we have a lot of work to do on the subsystems, and that's the intent of where we're going with SHIELD. Next chart. So other trends, what we're trying to make sure of is that we can get rapid system upgrades. There's been a lot of work on components in order for us to be able to exploit the modularity that's common in research and development design for use on these tactical platforms. We, as well, on that laser weapon system module program, we tried to get a module that was as common to all of the environments as possible so that we could swap out the particular elements that needed to be targeted towards the environment for that, that platform. And we have been working on ease of maintenance. And actually, I know a lot of performers have been working on ease of maintenance. I've seen pitches from them that indicate that we have a handle on what we need to do to make this reliable, maintainable, and available. So, as I said, the laser is no longer the footprint driver on this, and it may no longer be the performance driver. What we need to do is emphasize on getting a beam control system that can exploit the best aspects of the lasers that are available to us, and getting that power to the target. And so, since we are approaching lunch, I am going to stop there and allow you guys to do some questions.
Not because your slides disappeared.
Okay, we'll open up to questions from the audience. Yes, sir.
Hello, sir. My name's Mike Pearson. I'm with Booz Allen. It's been very educational today, and we've talked about TTP a little bit. You know, doctrine TTP, certainly a big part of this. But what energy has been put towards the countermeasures that we would anticipate against these systems that we're developing? Because we're out in the public domain, other people are doing it. We're certainly, you know, up front with us trying to develop the systems. Our adversary is going to try to figure out how to defeat them, or at least how to counter them. So what effort as part of our developmental process works the other side of that equation?
So I'll start. So at AFRL, I mean, we have a significant research effort on the defensive side of the house. Mainly it's housed in our Materials and Manufacturing Directorate. And just looking at various laser hardening type of materials, both for sensors and for other structures of air platforms, as well as space platforms. So totally understand the threat side of the house, and it's important that we conduct research in that area as well.
Dr. Killian?
Well, not so much at ONR. When I was chief scientist for the Army, there were a number of programs that we were doing on laser protection for systems. Again, primarily materials related, looking at protection of sensor systems and weapon systems against potential laser threats. I'm not as familiar with what might be going on in ONR itself in that subject right now.
If I could add one note, and Keith remembers this, we had a pretty intensive effort at MDA looking at, in conjunction with AFRL, looking at how you could counter the ABL in terms of coatings and things like that. What was interesting about that is it showed us why it was critically important to have actually full-scale testing, because there were some interesting effects that took place with the laser and some of these different countermeasures. But we looked at quite a few.
So one more thing on that. I mean, there's been a lot of talk on materials, but it's really difficult to harden an overall system to the degree that's necessary for you to be able to combat that laser. The laser has a lot of choices for aim point, and you have to harden everything in order for you to be able to get it. So it can be pretty expensive to harden the system. Right. I know that there has been really good work on getting to materials that have low absorptivity or high reflectivity or high thermal conductivity that allow a system that if you hit it in that point is going to be able to survive for a lot longer. But there are other points on the system, and what we need to do is make sure that we do our homework with regard to what's vulnerable on particular targets that we are interested in.
Hi, thank you. Sidney Friedberg, Breaking Defense. You know, we hear on this panel and from lots of other people here, you know, that we really are on the cusp. We have a system out on the Ponce. But, you know, I also hear Mr. Englander talking about, I think, tech readiness level 3 or 4, which is, you know, a long way from field ready. I hear, you know, discussions of the laser system, the 100 kilowatt system being, you know, still at 20% efficiency, which quadruples or quintuples, I guess, the total size, weight, and power of the system. So, how close are we to fielding different things, ranging from the dazzling laser to a self-defense laser that can shoot down an incoming AMRAAM, for example, to something that's for missile defense, to something that is, I don't know, blowing up hard body reentry vehicles that is at the extreme end of the spectrum. What's the timeline to get up that spectrum of laser capability?
Well, I think from an MDA perspective, I mean, we're operating at, our threshold is a much higher power level than what I think are some of the systems that are out there right now. So given that, I think somewhere, the current projection is somewhere around 10 years out or more to get up through all the TRL levels, get all the demonstrations done, to get the confidence, and also to get a platform located or identified for operating at the high altitudes that we're talking about.
I would say from an Air Force perspective, if you look at the SHIELD demo, when that's complete, let's say in the early 2020 timeframe, we would have, given that it's successful, we would have demonstrated at TR level 6 the capability to be able to integrate a medium-powered laser in a pod that can be put on a 4th or 5th gen aircraft. And again, that would the power levels will give you a more of a self-protect anti-sensor capability, and so then it'd just be the will of we're going to go into a program of record or not following that demonstration.
And I guess on the Navy side, well, if you want to talk about dazzlers, take a few of those off-the-shelf pointers you saw earlier, bind them together, turn them on all at once. It makes a pretty good dazzler already. And in fact, those types of systems have been used operationally. Clearly, we are currently demonstrating a capability in the 30 kilowatt class. And a big challenge, in fact, is the energy systems to support that. Now, in addition to doing the SSL-TM work, the laser itself, for sort of the next generation, in parallel with that, we're currently investing in architecture work, power storage, power conditioning, power management technology as part of the Future Naval Capabilities Program that will support systems like the high-power laser and the EM railgun in terms of actually providing you the necessary energy storage and management to support those weapon systems. And you're talking about things in the early 20s in that kind of power class and in terms of what you need performance-wise, I'd say. Beyond that, I won't speculate for right now.
So an obvious follow-on question to that may be, if you double the money, can you have the development time?
You want to take a shot at that, Rich? Would you like double the money, Rich?
Yeah, so right now, and I shouldn't say this in a room of contractors, I'm having all the problems I have expending my money right now. So we do have a lot of advancement going on in the lasers. There are things that need to be done on the beam control system and on the integration that I know are hard because we went through this preliminary design effort when I was at DARPA. I don't know that if you doubled the budget that I could even shrink the schedule by 20%. We need to know more about how the maturation is going, and we want to be as careful as possible about rushing into this and finding that we have just another interim system that's not going to be good enough to even have a residual operational capability. So I'd be careful about that. I do need to say that General Masiello indicated that around the 2020 timeframe that we should be ready to determine whether or not we can go forward with a high-power system. And as my boss's boss, I'd say, hoo-ah, I'm ready to go.
Can I just piggyback on what
Sure. Rich
said? First of all, I think AFRL is very well resourced given the current climate that we have, sequestration notwithstanding. We have great support from senior Air Force leadership, OSD, and the Hill. For our laser program, we have partnered with DARPA, and Dr. Mangano's here, great partner, and really, what's one of the biggest risks? The biggest risk is that we fail. Already it's been mentioned, there's a lot of stink over directed energy, over promise, under delivered. So I think what we built a program with sufficient risk, we're advancing the technology commensurate with a realistic technology maturation schedule. You heard the warfighters this morning, they want it faster, they want it now, but really, I don't think, especially in these initial stages, maybe when it came to a program of record, sure, we'd love to see a doubling of the budget. But from these initial stages, as we're walk, or crawl, walk, run, I don't think more money would necessarily be helpful in this situation.
Okay, other questions?
Yeah, hi, James from Flight Global. This question specifically for the Air Force. As the leaders of the active denial system, that's something that you have in the lab that perhaps hasn't been fully utilised because of the psychological impacts and the political impacts and various other reasons why you don't want to fry people under the skin. But do you think the time is upon us where we might actually see a functioning airborne version of this type of system as AFSOC wants?
Well, I'd say, yes, I mean, we would love to see it transitioned. I mean, anything we work in the lab and when we mature it to that level of maturity, that's our measure of success. Really, our overall measure of success on anything we work on is that it actually gets fielded. But like you mentioned, there's some different political and policy barriers, but we're still in discussions with AFSOC about integrating it onto some sort of C-130 platform. So, overall, I'm hopeful that we're able to do that somewhat soon.
Okay, next question.
There's been a lot of talk about accelerating programs and doing things a couple years faster than we thought, or I think, Dr. Bagnell, you mentioned about inserting technologies sooner. So is it feasible to think that we could have architectures that would allow us to do that so that the government perhaps could enforce like an architecture standard for systems? Would that be feasible, or are they all just one-offs? Is it feasible to have these drop-in architectures?
Yeah, so as I mentioned when I was talking about laser weapon system module that was worked at DARPA from 2012 to 2013 about, that architecture was not only modularized from a subsystem aspect, beam control, power, thermal, and the like. Inside, it was modular as well. And there were opportunities for us to exploit technology development in each of the modules with interfaces defined for us to be able to exploit those advances. So yes, it is feasible for us to do that, and it is feasible to do it in a common architecture that is usable in air, sea, and land environments. But we got to preliminary design, and we need to get way past that in order for us to assert that it is done, right?
Question in the back.
Yeah, I think you all can hear me without the mic, maybe. So, Dr. Bagnell, you've been mentioning some components that are more advanced. By the way, Sam Smith, Brad Whitty. One thing we've seen, though, at least on the UTC side, between UTAS, Brad Whitty, and others, is the systems approach, and that maybe we're lacking that. So I guess maybe a question for not that we're lacking that, it's a challenge. Question maybe to General Masiello is, where do we see the government's role, specifically AFRL or maybe ONO or any of the other agencies? Are you the integrator? Is it the prime that you're contracting with as the integrator? Obviously, we say that cooling is the big issue. How does that work, and how are we talking to each other across the board?
Well, I see the demonstrations that, especially SHIELD as the initial demonstration, really that's all about is integrating the various subsystems into some sort of workable whole. But at the end of the day, like I said, it's industry is going to build an integrated system and integrate it on the platforms. It's not the government. I think our job is to kind of facilitate it, provide the funding, provide the overall direction, but no, I don't view, especially if we're going towards an operational system, that the government is the integrator of these.
Yeah, I think from an MDA perspective, I agree with that approach. The government role would be to integrate that integrated platform into the overall ballistic missile defense system, so it would operate with the other tiered systems that we have, the mid-course and the terminal. So that would be our role.
Okay, one more question I think we have time for.
Bill Sweetman with Aviation Week. The whole of air combat history has really been about putting weapons on the target, from the Fokker triplane through the AIM-9 through super agility. It seems that you can fire a laser in any direction and you can't evade it. What happens, at what point, and how do we manage this process where you just say, well, we've got a lethal laser on an aircraft, possibly a large one, and this has turned everything on its head, and how does that affect the programs that we're planning, the things we're planning to build for the next 15 to 20 years?
Yeah, good question. Who wants to take that one? I mean, we don't call it a game changer for nothing. I mean, it truly is. But to get to that point, there's a long way to go. Even when I talked about the first step, having a pod, that's not even fully integrated into the air platform. I mean, we're talking decades to have some sort of 300 kilowatt laser possibly integrated into a fighter type platform. And then you also have the work that we're doing as a defensive side, but at this point, I mean, who knows? It could upend everything.
I mean, I think from our standpoint, it complements the rest of the system, since no layer of the system is going to be perfect. So the idea is that it would thin out the threats at a high rate, and then also would allow anything that we get through would be cleaned up with the rest of the system. So I see it as complementing.
Anybody else? So let's thank the panel. I thought they did a great job in giving us information this morning.